Hai fatto un'operazione così anche per le altre aree, no? Cioè, i CER sanno che non posso prendere lo slot.
Cioè, sono genera profonda e dalla mattina io mi metto lì a vedere quali slide arrivano, se arrivano.
Operazioni così anche per le
Chiudi,
altre aree.
quando parti lo streaming, devi
I
chiudere.
CER slot.
Chiudi. Il stream sta continuando ad andare.
Ok, quello
Perché,
come facciamo a saperlo adesso?
come?
Ehi,
E per tornare qua, sulla PowerPoint, torni sulla presentazione.
no, come faccio a sapere che sto andando su YouTube?
Perché c'è scritto lì, questa riunione è in fase di trasmissione in diretta streaming. Ma quando ti si apre su Google Chrome, tu devi chiuderlo perché altrimenti crea loop.
Ok,
Perché tanto non è da Chrome che stai facendo lo streaming, lo stai facendo da Zoom.
dall'altro.
E Zoom è comunque aperto.
Ok. E
Perché
poi io a un certo punto per chiuderlo,
interrompi,
aspetta,
sì, fai destra, interrompi
allora,
condivisione.
tanto qua gli posso dire ok,
Sì, ok.
ok, poi
Interrompi
interrompi
condivisione.
condivisione, però mi interrompe la condivisione delle slide, siamo ancora su
E
YouTube.
quando chiudi Zoom.
Ah, devo chiudere Zoom.
In realtà puoi andare anche su altro e interrompere.
Ok.
Comunque
Comunque tanto Zoom serve solo per i keynote.
esattamente, quindi
Ok,
puoi
quindi
chiudere
chiudo
Zoom.
Zoom e chiudi tutto.
Vabbè, adesso per fare interrompi condivisione perché tanto.
Ci serve? Qua posso chiudere?
Perché non lo so, io nei streaming dal vivo su YouTube.
Fermiamo qua.
Non c'è. Eh, adesso. Ah sì, se vuoi uscire, ricordo, se vuoi uscire però qua e
Sì,
sì, ma il cursore deve cliccare su questo schermo.
devi proprio
Sì, altrimenti non capisce. Adesso qua, sì, puoi chiudere e farti dare le sue slide.
Do you have your slide?
Ok.
Questo qua è per il...
E per il pointer fai copia e incolla della presentazione perché c'è solo una presa USB libera.
Non è uno.
Ah, it's USB-C.
It has both.
E both. Fantastico.
Mhm.
Yeah.
Qual era che detta questa? No, lo stesso.
Vai qua, vai qua. Apri da qua. È più semplice sempre se usi le esploro risorse.
Ok.
Unità 2009, una USB.
Spegni.
No, cliccaci sopra, cliccaci sopra.
Sì, no,
Devi aprire, poi vai su
io
IP.
non ho preso le slide, volevo solo
Ah,
togliere la privetta
ho capito,
in
chiudi.
modo
Scusami.
educato.
Allora va bene quello che stai facendo, non avevo capito. Fai
Solo che non so come si...
espelli.
Questo.
No. Come si chiama questo? Scusami.
Ma scusami,
Sakai.
comunque sul mio computer se tu lo trovi qua,
Puoi farlo da
poi lo
lì?
fai qua, e poi in teoria qua te lo fai espelli.
Mhm. Non vorrei staccare la roba
Sì, sì.
collegata lì.
Ok, mi facciamo tutto.
Sì,
Adesso
sì,
iniziamo. Poi sono queste. Però è un PDF, sarà uguale.
Più o meno sì, devi solamente fare.
Torno alla riunione.
La riunione sta andando. È là.
Io qua però ci torno.
Ah,
O vado giù. Ah,
vai
ok,
direttamente là.
ok.
Continua a essere aperto adesso, devi semplicemente apri PDF. Da qua, apri il PDF da questo
No,
schermo.
domani io prevedo. Ti mando un messaggio se funziona.
E schermo intero.
Ok.
Modalità schermo intero, quella sotto.
Ok. Ah, sì, è struttura viva.
E non lo so, è ancora un'altra roba, non lo so. Adesso puoi andare di qua, fare condividi schermo.
Riprendo quel-
Esattamente.
Se voglio vederla tutta, non mi dire niente adesso.
Si vedrà tutto qui più.
E non me la dà l'altro.
Come?
E questo?
Sì. Ah, non ti compare, vero? Perché non c'è
No.
la presentazione. Vabbè, c'ha senso.
Allora,
Tanto
I went to your slide there, but your slide are here.
here and here, and they will see them on streaming.
Okay.
Hello?
So I will see this. For, I don't know.
Okay,
Very
yeah.
good. I mean, that's,
It will be like this.
yeah.
GP.
I think I will see it.
Bello
So,
bello.
then use the.
This
one?
Yes, but
It works, it works.
you have also this one.
Okay.
Yeah, it works.
Yeah.
Which is fine.
Okay, here everything is
No,
ready.
perché ieri praticamente ti ricordi che c'era il break più breve? Che ne sono andata io perché ero preoccupata che fosse in ritardo e io non sapevo lo streaming come era settato. Io ho messo solo le slide.
Poi glielo chiediamo se vuoi.
Cioè, io avevo saltato lo streaming, ma non avevo la presentazione su.
Esatto,
Quindi non avevo fatto
infatti, cioè,
Era per quello che avevi scritto.
Io.
no, questa è un'altra roba che non riuscivo a mettere le slide là, vabbè, non importa. Però pazienza, nel senso, solo che appunto io non avevo seguito lo streaming e quindi, però lei ero già qua che smanettava, quindi anche lasciare i team anche da soli, cioè, non è proprio...
Tanto adesso
Vabbè, comunque glielo dico io magari.
sì, sì.
Ma adesso su YouTube tutti insieme, tipo, i keynote.
No, sono dei video separati.
Sono dei video separati, ma cioè, possiamo anche toglierli volendo.
Adesso si stanno vedendo solo.
E allora chi se ne frega, cioè, non diciamo di perché non abbiamo chiesto loro.
Esatto, è stata chiesto una liberatoria, penso, per questa fine.
Anche secondo me, quindi togliamoli e basta, non dobbiamo neanche menzionarla.
Li tolgono da solo.
Ecco, allora basta.
Perché
Io
non-
direi anche adesso se si potesse, ma...
Non so se si possa fare.
Pazienza, però secondo me non fa neanche tempo a guardare.
Sì, no, ma non ti preoccupare. Comunque tecnicamente non dobbiamo più parlare di questa storia con queste cose, perché ci sono i cartelli fuori che dicono se si passi questa linea qua dello use, tu senti essere registrato. Non li avevi visti?
No, neanche.
Sono giù da basso.
Allora facciamo la foto dopo, vado in banga video.
Se vado un attimo a pigliarmi un cappuccino.
Bravo.
Mi raccomando, prendi le uova, ragazzi.
E ova. Cosa? No.
No che restare in collega in Buenos Aires. La situazione
Yes, I would say.
we have
I help you very much, yes.
we go to that environment.
Yes, yes.
Said they like this nice thing.
Mhm.
That's not real. International government said you have to come over here. Yeah, what you do there. And so, it's fine.
This is where.
So spend 6 months making all the clients, or you do just always, or in the winter. So
Okay, yes.
I generally go there,
Yes, I.
and the airport was
Yes.
closed
Oh.
for 6 months.
Are you ready?
Yeah,
I'm ready.
And so we had to move it. We were saying
Oh.
in 2 months it will be open. In 1 more month.
Yeah, I think it should take 15 minutes.
Okay.
Because I have this all just recalling the structure, so it's not for 57 slides, it's 45.
Yeah, I'll have the 5-minute thing. But I guess I won't need it if you only go for 50.
No, I think it should be 50 minutes.
Cool. Well.
Okay, okay.
It's better to have more than rather than less time and
Yeah.
don't worry, and also I'm sure nobody, that's whatever is the brain.
Or the rather more time.
So, yeah, it's very well.
So hard because there's no wind.
Yes, it's like very sticky.
Huh?
It's very sticky.
It's very
Damp and, yeah.
I don't have any problem anymore. So. Depends.
It's a very effective fan.
Yeah, I gave it to Marco because he loves quiz.
So the question. There was a series.
Vai Edoardo. You speak it, no. No. Yeah, let's go. Let's go.
Io come va?
Io il tablet, Tablet. Questa sera. Quindi, se non è too much. No, adesso. Per ora, no? Sì. Ora dobbiamo averla qui, sì. Di ieri. Niente parla, nosotros no.
Già non esiste questa conferenza.
Sì, in Colombia, che riti mi invitavo, io ho visto io.
Non lo sai esattamente quello che passò.
Sì, nero.
Sì, però sì, no, però non sembra che continuare, no, però avrei risposto in inverno, non avevo contattato.
Fue en enero.
Sì,
este
sì.
año.
Fuori.
Infatti adesso guarda, non c'è aria proprio. E tu non mi hai dato il programma, quindi devo.
Ma hai
Ho
dato il tuo?
procurato un'altra cosa, hyper planning.
Io pensavo che tu me l'avessi detto.
No, io ti ho dato il mio.
Ah,
Mi
vabbè.
sono sacrificata.
Ma dove sei? Che te ne ho fatto? No, io ho perso il mio, allora ne ho chiesto uno, l'hai mandato tu.
Mi sono
Lo sai che non c'è?
sacrificata. Questo qui è due adesso.
Ah, ecco, ho capito adesso. Vedi che sei all'origine. Chi è all'origine del problema?
No.
No, però oggi c'è ragazzi. Per me perché ieri contattavo una
No, ma
Io mi faccio la qualità del
abbiamo anche questi cavalieri di una roba proprio demoderna, però ce l'hanno.
Sì, avevo trovato una critica da farti, ma poi l'ho esposta a loro tre, mi hanno detto, mi ha detto che no, che non va bene, che avete ragione voi. E quindi devo ritirare questa critica. Ho pensato per 2 giorni, finalmente ne hanno trovato una, e loro tre mi hanno subito massacrato. Io ho esposto questa idea, ma
Non ha funzionato.
non ha funzionato. Ho scritto.
Since you were saying that you are, we can also wait a couple of minutes if you want.
Yeah, I think we should take in 50 minutes.
We can start at 02 or something, but I don't want to start too late because of the streaming.
To just start 2 minutes.
Ho scritto per.
Maybe just like, so if people are a bit late. I think the streaming should be all set up. Yeah, it's in.
Scritto per la tua casa?
No.
Ho chiesto nei 20 giorni che restano.
Speriamo.
Dovete
C'è scritto nell'email esattamente per ovviare questi problemi.
Allora, attualmente cioè io ho letture, sempre letture selettive.
Scriva apposta che così andiamo e ti mando la sì.
No, fa niente, per adesso non ti dico dei nomi.
Sì, perché pensavo di andare a lavorare così, anche Kenny mi lascerò così vado anche il
Any Israel.
Non lo conosco.
ma come no? Io non sono per te lo presento, io sono un po'
Sarà la mia rapporto con OGS.
è l'ultimo fino. È l'ultimo
Ho capito.
Vabbè, era
Ho sito a parte.
infatti è scomparso già
Che è successo? Non lo so, secondo
non mi
me.
dispiace che non è
Magari appunto sono sì.
Ma lui dove sta?
Adesso stava a San Francisco.
Vabbè, la madre dove sta?
No, la moglie da un'altra parte. Adesso non mi ricordo esattamente, ma sì. Lui ha passato parecchi mesi quest'anno insieme al lì e con lei.
La foto di gruppo, per quel momento dove ci sono tutti la gente. Ma dopo il problema è che dopo il show i giovanili hanno gli altri,
Già in sofferenza.
perché non so per non so se
Vabbè, decidiamo dopo, vediamo che chi arriva, non
Andrea mi ha mandato la foto che fa, quando ho messo su Broletto.
Guarda,
Ieri. Stavo parlando.
I think, yeah, we can move forward. I mean, it is. Yeah.
No, stavo
Yeah, otherwise.
chi hai un investigatore?
All right. Good morning. Good morning, everyone. It's the last day of spring or the first day of summer? Which is it? Does anyone know? Okay. It's the last day of spring. Anyways, enjoy this last day of spring. Tomorrow, summer begins. This is just a prelude. So it's my pleasure this morning to be introducing Eduardo Giovannini. So just to say a few words, Eduardo received his PhD from the University of Buenos Aires in philosophy. He's also studied in Vienna as a Lisa Meitner postdoctoral fellow. He's currently an associate researcher at the National Scientific and Technical Research Council and an assistant professor at the Universidad Nacional del Litoral in Argentina. His research is in the history and philosophy of geometry and in logic as well. He is particularly an expert in Hilbert's Foundations of Geometry, although he recently published a book on the theory of plane areas. Right, that's published now.
No.
Not published.
No.
Okay, I was looking at,
No.
it wasn't clear.
It's yeah.
Forthcoming.
It's yeah. It will come
Okay.
out eventually.
Look out for it
Yeah.
soon. Today, we're talking on the foundations of geometry and the science of magnitude in the latter half of the 19th century. So thank you so much.
Thank you very much, Emma. Well, first I would like to deeply thank the organizers of the meeting, Silvia, Andrea, Guido, Ludovic, and all the organizers for the invitation. I'm very honored, and also the scientific committee. So the APMP, these meetings have been very important for my academic development, for the way I try to approach the philosophy of mathematics. So I'm very honored by this invitation. So thank you very much. So moving to the presentation today. So the topic of my presentation, it's in a way a very classical topic in the history and philosophy of late 19th century mathematics and early 20th century mathematics. And there is this debate or discussion around the role of magnitude for the foundation of mathematics. But I will try to focus this topic from a different angle, and I hope that this could suggest some new ideas of what was the significance of this debate for late 19th century mathematics. So as I was saying, we know there is this provocative image that is often invoked to try to describe the profound transformation that mathematics underwent during the 19th century, and this image that it was at the end of the paradigm of mathematics as the sign of magnitude. This expression is by Maurice Epler, really nice paper. And of course, by this expression, he's referring to this influential trend in 19th century mathematics that tried to eliminate this sometimes vague concept of extensive magnitude as a unifying framework for all mathematics. Well, this attitude was really crucial, a cornerstone in the program of the arithmetization of analysis, at least in the line of represented by Weierstrass, Cantor, and Dedekind. For instance, well, this idea was really clear in Dedekind's work on the definition of irrational numbers in his classical work on 1888, and we come to this famous, really well-known passage where he explicitly stressed this point. So Dedekind says, for the way in which the irrational numbers are usually introduced is based directly upon the conception of extensive magnitudes, which itself is nowhere carefully defined, and explain number as the result of measuring such a magnitude by another of the same kind. Instead of this, I demand that arithmetic shall be developed out of itself. So essentially, this is very well-known idea. So the rejection of the concept of extensive magnitude was fundamental aspect in the set-theoretic construction of the real number in the last 3 decades of the 19th century. But as we also know, there was a reaction to the arithmetization program that still aimed to vindicate the concept by offering a rigorous abstract axiomatization. This is what is known as the abstract theory of magnitude, or
or Grothenlehre, which was also developed at the same time. And we know the main idea here is that, well, just using the merging of the modern axiomatic method, if we could provide a rigorous axiomatization of the concept of magnitude, it is still a very important mathematical concept. And in this sense, they oppose to the arithmetization line. Well, I think there is a very, very rich literature on this debate that explores and discusses historical, philosophical, and mathematical problems related to the role of magnitude. But essentially, this literature is focused on the foundations of real analysis in the late 19th century and in the early 20th century. And also, there's also important literature of this topic in connection to the emergence of modern measurement theory, the work of Hölder, then later Campbell, and so on. What I've tried to do today is to revisit this classical debate on the role of magnitudes for the foundation of mathematics, but by focus on a different mathematical area. That is the modern investigations into the axiomatic foundations of Euclidean geometry. So if this discussion has any implications for the emergence of modern axiomatic geometry, by this I mean in the late 19th century. The motivation for this is that one of the motivations is that since these notions of intensive magnitude serve as a unifying framework for all mathematics in this period, so it's reasonable to think that this debate must have influenced other areas of mathematics, not only the foundations of real analysis. And also, since also this debate contributed to the formation of the concept of a foundation of a mathematical theory in this period, so one can think that it might have been also relevant for other foundational enterprises during this period. Well, and I would like to essentially propose two claims to explore two main ideas. The first is that the debate about the role of magnitude in the foundations of real analysis had really significant implications for the modern axiomatic investigation in the foundations of geometry, particularly in the synthetic tradition. There are some historical points which are related to this claim. So first, I think it's interesting to observe, if this is in a sense correct, is that it is interesting to know that the idea of a new independent foundation for Euclidean geometry was strongly influenced by a foundational debate occurring in a different mathematical field. So one often read that, well, this program of providing a new strictly synthetic or independent foundation of Euclidean geometry by the end of the 19th century was deeply influenced by the merging of synthetic projective geometry in the program. And of course, it was really important, but it's also interesting to know that, well, this program in geometry was also related to other mathematical fields. And also, well, the geometrical program that aimed at a new synthetic foundation of Euclidean geometry, if this is correct, should share a common purity concern and an autonomy ideal with another foundational program which went exactly in the opposite direction. So the arithmetization of analysis tried to eliminate mathematical considerations from the foundations of analysis. The geometrization of geometry tried to eliminate analytical assumptions, but both programs aim this purity concern about eliminating the concept of magnitude. But I think it's one of the main challenges is try to explain what does exactly mean, or what were the tasks of eliminating magnitudes from the foundations of geometry, in the sense that for the case of analysis, it was clearly articulated by the main proposals, but in the case of geometry, it was not that clear which were exactly the task. And So the second claim is that many key structural transformation in Euclidean geometry in the later half of the 19th century were connected to this demand to remove the appeal to abstract or to general magnitude from these foundations. Now, what I want to suggest here is the shaping of modern axiomatic Euclidean geometry not only involve the construction of consistent and mutually independent and complete set of axioms, which prove adequate to prove the main results, but also involves, from a foundational point of view, it involves a reconfiguration of the central parts of the theory of elementary geometry, how the theory of congruence, plane area, proportionality, similarity were related. These reconfigurations, I would like to suggest, was intimately connected with this demand of avoiding the classical or circumventing the classical theory of magnitude from these foundations. These are two basic claims. So first, just to finish with the introduction, a terminological note. So part of the complexity of this debate is that the term quantity of magnitude, the reference or the meaning was in flux in the second half of the 19th century and were often used ambiguously. So to kind of avoid this, I will stick to one distinction which was already now clear by the beginning of the 20th century. And so I will use the term magnitude or magnitude type to refer to a property standing in relation of being greater or less than something. So length, area, volumes, distances are examples of magnitude. And quantity will be the entity that has or possess a magnitude. So a line segment, a plane figure. And then the other term is what's general abstract magnitudes. So these are different sorts of mathematical entities, geometrical magnitude number, but also masses, temperatures, which can be joined, separated, or compared, but whose further nature is left unspecified. Concerning the structure of the talk, I will say some really general things just to provide a context about the arithmetization and this idea of the end of the sign of magnitude. This is not really novel, but just to provide a context. And then I will focus or point out what I think were the consequences for this geometrical debate, these geometrical echoes. And in the first place, then I will try to show how these ideas, these challenges were addressed by the modern axiomatic foundation of geometry, in particular in Hilbert's work. And it was this idea of developing a geometry without general magnitudes, and then with some final remarks. So we will know this. So until mid-19th century, it was still very common to conceive of the fine magnitudes as the sign of magnitude. So in this sense, it's the general concept of magnitude provided a unifying framework for all mathematics. And for instance, this is very clear in this important book by Euler, The Elements of Algebra, where at the very beginning of the book, in the very introduction, he characterized mathematics as the sign of magnitude. So he says the following, whatever is capable of increase or diminution is called magnitude or quantity. From this definition, it's evident that the different kind of magnitude must be so various as to render it difficult to enumerate them. And this is the origin of the different branch of mathematics. Each begin employing on a particular kind of magnitude. Mathematics in general is the science of quantity or the science which investigates the means of measuring quantity. Of course, essential to this paradigm, this was a conception of numbers defines in terms of the idea of magnitude. So a number presents in itself a relation or abstract ratio between one magnitude and another considered of the same kind, considered as a unit. This is a very famous definition of number provided by Newton. I think it's pretty well known, so it's not necessary that I read this. But this image changed profoundly during the second half of the 19th century, and this is what Eppler in this article calls this changed the end of the paradigm of mathematics as the science of magnitude. Very, very roughly, there are several parallel developments or events initiated this departure of these paradigms. The emergence.
A bit closer because let's say
yeah.
like exactly.
Okay.
It's a bit not right.
Okay. Now it's a little better.
Yeah, I can
okay.
put it here.
Okay.
Yeah, perfect.
Thanks, Livia. So one of these events, so the merge of the tradition of symbolic algebra in Great Britain, so the work of Peacock and Morgan, in which symbols of algebra were no longer interpreted as represented necessarily numbers or magnitudes. Also, the gradual extension of the concept of number in the work of Kummer, Grassmann, Hamilton, and many others. Hamilton quaternion, so they don't fit very well with the idea of the classical idea of magnitude, or as we saw in the first conference about Karim, this idea of Kummer. And another development, so the formation of the mathematical concept of manifold in Riemann, of multiple extent magnitude, which transcended the framework about Ehrlich's ideas about magnitudes. So by constructing entities we could no longer reach of sum under the traditional notion of magnitude, this development exploits, so to say, the extension of the concept. But of course, there were technical issues in the field of analysis that threw up difficulties that also undermine the extension. This is a process of, the rigorization of analysis, so proof of basic theorems concerning limits process, such as the convergence of sequences of functions, show that there was the need of a clarification of the notion of a real continuous magnitude. This was urgent. And this very broadly, so this result of this process led that the concept of set on real number replaced the 18th century concept of magnitude as the general framework for the foundations of real analysis. So, was proposed by the hermetization of analysis, so the appeal to the notion of magnitude should be replaced by a strictly arithmetic construction of the real numbers, often the natural or the rational, which were less problematic than the notion of extensive of measure of magnitude. And this should be accomplished using a general strategy was to carry out a successive or step-by-step construction of the real system by purely arithmetical means. So the purpose was to define more rigorously the basic concepts, in particular of rational numbers, which previously were justified only via geometrical considerations, but also a crucial aim in refraining from the concept of extensive magnitude was that the arithmetizer also sought to promote analysis as an autonomous branch of mathematics by extracting it from the field on geometry. So there was a strong purity concern. But this position in the hermetization was not unanimous, and there was another trend that dispute this idea of hermetization. And in response to the program, there was a notable array of works that appeared at the end of the 19th century that aimed to prove the mathematical usefulness of the concept of magnitude by providing a rigorous abstract axiomatization. So the roots of these investigations can be found in Grassmann, Dubois, Mont, but also was very important contribution by Otto Stolz, Helmholtz, Betazzi, Burale-Forti, Helder, and many others. Very, very broadly, so for these authors, there were epistemological, pedagogical, but also foundational reasons that justify the attempt to achieve a rigorous definition of the real numbers in terms of ratios between magnitudes. So one epistemological reasons, also very well studied, so it's so-called the implication constraint, which in very broad terms prescribe that the very definition of the real numbers must account for its application to measure continuous magnitudes. It was very for Frege, Russell, and Weikert. So in this sense, this author prefer or the approach of the axiomatic theory of magnitude. Pedagogical reasons that will, let's say, for example, Burali Forte defense that one could explain, especially in secondary school, the general notion of number more clearly or in a more concrete shape if one start with a concrete idea of a magnitude, and also foundational perspectives. We're trying to uncover a common structure between numbers and geometrical magnitudes and establish the analysis between analysis and geometry. But this is a very broad context. So my main concern is, however, this has a fundamental significance for the foundation analysis, but also for the emergence of modern measurement theory. But this debate have any impact on the development of modern axiomatic geometry by the end of the 19th century and the beginning of the 20th century. And I think it did have an impact. Basically, there are two mathematical developments or two places where we can explore the significance of this debate for the foundation of Euclidean geometries. The first is a rich area of work in this period, which search for an alternative foundation for the classical theory of proportions in the last decade of the 19th century. That is for a new theory of geometrical proportions. And the second place is if one study the reaction of the consequence of the abstract axiomatic characterization of extensive magnitudes specifically in geometrical text. So this is what I wanted to do next. So a purely geometrical theory of proportions, as I said, was in the late 19th century, another other works aim to provide a purely geometrical foundations for the theory of proportions. This is just a few works, but you can find really a rich array of works using precisely the same word, so the purely geometrical theory of proportions. So, for instance, Grassmann in the linear extension theory, but also the less geometers like Hoppe, Kupfer, Nesser, and many others, which were trying to construct a new theory of geometrical proportion. And also this was also very important in the mathematical, Italian mathematical community. Just to recall some very basic idea of Euclid theory of proportion, just to be the context for the critics in the 19th century. So we all know very well this in book 5 of the Elements. Euclid, our Eudoxos, provide an abstract theory of ratio and proportions among magnitudes. Here, magnitudes was a term for a generic denotation that refers to geometrical objects. So magnitudes are line segments, prime figures, for instance, inasmuch as they were considered as to their size. And of course, to overcome the problem of incommensurate magnitudes, Euclid developed, or Eudoxos, a theory of comparison of ratios. It could be applied both to commensurable and incommensurate magnitude. But at the very base of this theory is the conception of magnitude. So this conception of magnitude, Euclid builds the theory, the foundation for the theory of ratio and proportion. So the very core of the theory are these two basic definitions. Definition 5 and definition 7. So I will just mention the first one because this is very well known. So two magnitudes have the same ratio with respect to two other magnitudes if taking m positive integers multiples a and c and n multiples of b and d, one of the following conditions holds. So this inequality, and in this way, just taking equimultiples, he can provide a definition of sameness of ratio, which is both applicable to commensurable and incommensurable magnitudes. But in order for this theory to work, there were several implicit assumptions about magnitudes that that you could just assume. So first, the comparability. So there is the existence of a linear order between magnitudes, divisibility, the existence of the four proportional, and the Archimedean condition. These are all assumptions about magnitudes. But what is crucial is that magnitudes are not numbers, so for this fundamental distinction between magnitudes on the one hand and numbers which are only the integers. One was just the unit, and ratios for Euclid, of course, are not numerical fractions. And this is very clear or essential in the fact that in definition 5, Euclid established a condition for an identity of ratios, not for equality. So we say that the ratios between two areas or two lengths are the same, but not equal, because equality only applies to magnitudes and numbers. And then in book 6, Euclid applied the theory of proportion to the theory of similar figures. So what was the main criticism to the classical theory of proportion in the 19th century? And I want to present some passages, some places, some references about it. So the first one is by Grassmann. And in the Ausländer, he points out the following. So an essential effect of previous presentation of geometry is that one usually returns to discrete numerical ratios in the treatment of similarity theory. And this procedure soon enough becomes entangled in complicated investigations concerning incommensurable magnitudes. To be sure, one cannot eliminate the problem of measuring spatial magnitude and expressing the result of this measurement numerically. To relegate the theory of similarity and even that of surface area to this branch, as has previously occurred, not to the form but to the substance, is to steal the essential content from what is called pure geometry. So in the next passages, you will see that the same idea, the same criticism, but basically what we have here is the idea that now the notion of spatial magnitude was identified with this measure expressed numerically. And by changing this meaning in the notion of spatial magnitude, they found that the classical theory of proportion did not have a purely geometrical foundation. So for instance, we have the same idea in Hoppe, which is also one of the first geometers that provide this alternative foundation. He points out the following there. As can be found in all textbooks, the theory of line proportion is still based on the measurement everywhere in school education. According to this, a linear ratio is nothing more than a numerical ratio. Here, it is not possible to avoid introducing the most general concept of an irrational number. On the other hand, then the theory in question is not a purely geometrical one, but rather transfer an arithmetical theory to geometry. On the other hand, this arithmetical basis proved inadequate. It must first undergo further development in order to fully fulfill its role in geometry. So again, the same idea that the notion of geometrical magnitude was identified with the numerical measurement. And in this sense, they found that, well, the classical theory has an arithmetical rather than a geometrical foundation. Okay. Well, I will skip this, but in Hilbert's now collector courses, you'll find again same idea that the proportion was just a numerical equation in the classical treatment. So to sum up, the critics saw a widespread assumption was the identification of geometrical magnitudes with the measure expressed numerically. Anthony Malay, in a paper from 2006, showed that this informal numerical understanding of continuous magnitudes initiated already in the 16th century. And so since Euclid's definition of sameness of ratios should be understood as the quality, or was understood by them, like the 19th century geometers, as the quality between two numerical ratios, the theory of proportion rests implicitly on the concept of irrational number. And Euclid's classical theory for these geometers had an arithmetical rather than a geometrical foundation. So the demand was to provide a new foundation for the theory of proportion independently of the theory of magnitude, and in this way just eliminate foreign elements. So one can see here the connection with the concern in the arithmetization of analysis. This foreign element was based or represented by the identification of geometrical magnitudes with numerical measures. So the goal was then for the new theory of geometrical proportion first to provide a strictly geometrical foundation of this theory in the sense that one has to explain geometrically what does it mean that two pairs of geometrical entities are in proportions. In other words, to develop a theory of geometrical proportion independently of the theory of abstract of general magnitudes. And this was done specifically by developing a theory for line segments. So a theory by providing a rigorous definition for the proportionality for line segments. And an additional important condition, and this can be noticed very clearly in Hilbert, was that in the construction of this theory of proportion for line segment, one should avoid the use of the Archimedean axiom, which was an essential assumption in Euclid's theory. But what about the implications of the immersion of the abstract theory of magnitude for geometry? So as I said early, so a fundamental motivation for the axiomatization of abstract magnitude was to produce a rigorous definition of real numbers as ratio of magnitudes. And there were epistemological, methodological, and pedagogical advantages over the arithmetic analysis. But what were the consequences for the foundations of Euclidean geometry? Well, first, the emergence of the abstract axiomatic theory of magnitude contributed to clarifying the concept by specifying its algebraic structure. Now we have a more clear explanation of the concept, and there were many different axiomatizations during this period, but usually, so it was characterized as a combination of an ordered and an additive structure, and what we now understand as in modern terms as an ordered additive semigroup. But I think that the existence of an explicitly formulated axiomatic theory of magnitude prompted issues key issues for the new axiomatic foundation of Euclidean geometry. So first is how, now that we are axiomatizing Euclidean geometry and we have an abstract axiomatic system, but we also have an axiomatic system for magnitude, what should be the relation between these two axiomatic theories from a foundational standpoint? This was a central question for the geometers trying to axiomatize Euclidean geometry. And the other question is, do the axioms for abstract magnitude impose constraints on the very formulation of strictly geometrical axioms? And this second question will be more clear in a minute, what I mean by this. And I hear an answer to these questions can be found in the following remarks, but also by these geometers working in this period. So for instance, Friedrich Schur has a very short but an important paper where he studied the problem of the comparability of polygonal areas, and he wants to provide a proof that in order to have a total order for polygonal areas, you need to prove the fact that a polygon cannot be equivalent to a proper part, and that should be a theorem of geometry, not just assumed as an axiom. And this is what he says in this context. A problem as simple as the measurement of plane figures bounded by a straight line has not yet been rendered with the necessary rigor and purity of the method, as it seems to me from the available literature. Not even speaking about the illegitimate use of infinitive process, general axioms of magnitude are used without justification. For these are only immediately evident when the magnitude are straight line segments. But before one has not managed to measure plane figures by segment, which is only possible by the theorem to be proved. This is the theorem that a polygon cannot be equivalent to a proper part. The application of this principle of magnitude is by any means justified. So the idea is that in a rigorous axiomatic treatment of geometry, you cannot assume any more general principle of magnitudes. You need to provide a justification of a geometrical interpretation of these principles. I will clarify this idea in a minute. A similar idea can be found or it's expressed by Hilbert in his notes for lecture courses just before the publication of Foundations of Geometry. So Hilbert was here working with the formulation of the actions of congruence for segments, and then refers to that this relation of segment congruence satisfies the transitive property. And in connection to this, he makes the following remark. So often one encounters the conception, possibly Euclid held this view, that theorem like the one just proved, that is the transitive or the segment congruence relation, are pure magnitude relations and therefore do not require any kind of particular proof and should not be introduced as a specific geometrical accents. But this is not correct. This depends entirely on which relations I define as equal, congruent, and so on. And finally, just to wrap up this idea, I think though the point is perhaps Otto Hölder in his classical work on the action of quantities, of magnitudes, was the one who really clarified this issue, put it in very clear terms. So Hölder says, the theory of measurable magnitudes applies in the same way to the comparison of addition of time, mass, line segments, and area. However, so as to prevent any misunderstanding from the outset, I know that the axiom of the theory of magnitudes shall not be presupposed for geometry in the form presented here, by applying them to line segments and area. On the contrary, the axioms of the theory of measurable magnitudes satisfied by line segments follow from purely geometrical axioms for points and segments on a line. So to summarize the idea, I think that one can see here that the axiomatization of the concept of abstract magnitude also led to the elimination of the notion of abstract magnitude from the foundations of modern Euclidean geometry. And this elimination of the concept of abstract or general magnitudes consisted or involved essentially two main steps. First, general principles of magnitude should no longer be assumed as axioms, but converted into geometrical propositions by interpreting the relations and operation of magnitudes as specific geometrical relations and operations for every kind of geometrical object. So one need now to provide geometrical interpretations for general principles of magnitude. What does it mean that two polygons are equal? How you define the property of addition, and so on. And second, these geometrical propositions could now be taken as axioms, but plus a theorem from the axioms of geometry. And I think that this imposes a strictly methodological constraint on the process of axiomatizing Euclidean geometry. And why? Because you cannot, in the process of coming up with an existing axiom in a system of axioms, one cannot assume anymore as an axiom a proposition which is just the geometrical interpretation of a general principle of magnitude. One needs to provide a proof. So to summarize, then one can distinguish two main tasks involved in the process of eliminating the concept of general magnitudes from the foundation of Euclidean geometry. First, to develop the theory of linear propulsion independently of the classical theory of magnitudes, and second, to construct a strictly geometrical axiomatic systems in such a way that the axioms are adequate to guarantee that every kind of relevant geometrical entities determine a magnitude type. So, and this is this could be recasted by saying that this consists in removing the fundamental assumption. So what is the fundamental axiomatic assumptions that every kind of geometrical entity, just as lengths, area, volumes, are magnitudes. One need to provide a proof, an axiomatic proof of that. Couldn't be not assumed as an axiom anymore. So how were these two issues addressed by late 19th century? So I think, again, one can distinguish the two tasks. So first, the development of these modern theories of geometric proportions, and then an axiomatic theory of content. Well, for reason of times, so there is an axiomatic approach to this, basically represented by Hilbert, but also by Friedrich Schur, for instance, and a synthetic approach, which basically avoid the structure by Hilbert of deriving the structure of a field from his axioms of geometry. But so for reason of times, I will only focus on the axiomatic approach, but just wanted to mention that there was another alternative. So basically, how these issues are addressed in Hilbert's Foundations of Geometry. So Hilbert's new axiomatic approach involved a structural, one could say a structural transformation of Euclidean geometry. And schematically, this transformation was accomplished by means of three main steps. So the first is the development of a geometrical theory of numbers from his axioms, from his geometrical axioms, but without assuming the Archimedean axiom. The first step, it's called as the segment arithmetic. It's very well known. So the second step, based on this, so he provided a rigorous foundation for the theory of proportionality and similarity, based, as I said, on the construction of segment arithmetic. And then he reconstructed the theory of plane area using his previous result on the theory of proportion and similarity. This means that the theory of proportion and similarity were developed prior and independently of the theory of area. And this was a structural change with respect to the structure of geometry before foundations. And the key element was the derivation of a structure of another field from the action of Euclidean geometry, as we will put it in modern terminology. So we haven't seen this. Of course, we all know Hilbert's axioms for Euclidean geometry. He divided into 5 groups: incidence, betweenness, congruence, parallel, and continuity. In continuity, he distinguished between the Archimedean and his axiom of completeness. But what is more important to me, this is very well known, so is that Hilbert axioms are purely geometrical in the sense that they not only avoid any kind of numerical assumptions, but also they avoid the concept of general magnitudes. So the first step, in Foundations of Geometry, Hilbert proposed these 17 axioms that characterize a complex number system, which is actually the first axiomatization of an Archimedean order field in modern terminology. So this was the first step to provide or characterize the notion of, as we say now, an order Archimedean field. But what is important here is that this axiomatization was not intended as an axiomatization of the concept of general magnitude. This is not what Hilbert was trying to axiomatize there. So once he has the notion of an Archimedean order field, he proceeds to this construction of a geometrical theory of numbers, that is his segment arithmetic. Hilbert's construction of a segment arithmetic consisting in defining purely geometrically the operations of addition and multiplication of segments, and then proving that these operations satisfies the relevant algebraic properties. Now it satisfies all the properties of another field. Well, in strict terms, the elements of the segment arithmetics are equivalent classes of segments model congruence, and well, addition is very simple. And for the case of multiplication, Hilbert used for the construction, geometrical construction of the four proportional to define a multiplication. Now we know, and this of course presuppose that we have fixed a unit segment and the validity of the parallel axiom. But what was the novelty of Hilbert was that of the originality was the key realization that two classical theorems in projective geometry, the theorem of Desargues and Pascal, could be used to prove that these operations satisfies additional multiplication, all the properties of an ordered field. So in particular, the Desargues theorem was essential for the associative law of multiplication, and Pascal for the commutativity property. And in this way, Hilbert accomplished then a purely geometrical or internal introduction of number into geometry, in the sense that now its coordinates were now these elements of the field generated by the segment arithmetic. This geometrical derivation of the structure of another field from the structure of Euclidean plane was what allowed Hilbert to provide a new or an adequate definition of proportionality of line segments, and then to reconstruct the theory of similar triangles. So this is basically Hilbert's definition of proportion that uses the notion of multiplication. So if A, B, A prime, B prime are any four segments, so the proportions of A to B is equal to the proportions of A prime to B prime. They know nothing more than the quality of this multiplication. So now, as you see, very clear. So our ratio is an element of the segment arithmetic, and proportionality means equality of ratio. So basically, what we have here is that of Hilbert's idea is that starting from the definition of segment multiplication, he can regain the notion of proportionality of line segments, and in this way he avoids the reference to the axiom of Archimedes. So he starts with this definition, and in this way he can provide a new definition for proportionality. The central aspect is that the new theory of proportion no longer relies on the Archimedean axioms, and therefore it does not presuppose any numerical assumptions. So have 10 minutes. The last step, or the first step, so now he has the notion of proportions. He used the algebraic properties of segment multiplication to obtain or to prove the fundamental theorem of triangle similarity. That's the Thales theorem. And from this theorem, he's able to recover the main result of the theory of similar triangles, independently of the Archimedean axiom, but also from the theory of plane area. Well, I should note here that Hilbert's proportions only apply to line segments. So therefore, to recapitulate all the results from book 6 of Euclid's Elements, one needs to include the concept of content of a figure in terms of proportions. So I need to include also areas in proportions. Well, this has been observed and studied in Harshons and in Blasik and Iturenko in these references. So so finally, when the last step was just use the segment arithmetic, the theory of proportion and similarity to reconstruct as the last step the theory of plane area. And Hilbert used the arithmetic of line segments and the theory of proportions just to provide a rigorous development of the theory of plane area. In particular, he developed a strictly geometrical theory of area measure. But this is geometrical because now he defined these functions of area measure. We do not take numerical values, but just the values are elements of the segment arithmetic. And what was essential is that to prove that this function is well defined, he used basically the results on proportion and similarity of triangles. So to summarize, the structural transformation of Euclidean geometry consisting in providing a new geometrical basis for the theory of proportions, which could be used later to reconstruct the theory of similarity and plane area. And all these results were are based on the construction of the segment arithmetic independently on the Archimedean axis. So the derivation of the structure of a field from the foundations from the axis of geometry reveal how a theory of linear magnitudes resulted intrinsically from inside, in the sense that it didn't need to be imposed axiomatically from outside. This is, I think, that the key point where you can see that this paradigm of providing a strictly geometrical foundation for Euclidean geometry suppose this removing the concept of abstract magnitude. So I will skip for reason of time the second this other development, the axiomatic theory of content, and just go to some final remarks. So some very general final remarks. So first, so the elimination of the concept of general magnitude was a central aspect of the modern synthetic approach to Euclidean geometry in the last 3 decades of the 19th century. And I think one could see from this development is that the idea of an autonomous foundation for Euclidean geometry emerged in connections with other foundational programs in late 19th century mathematics beyond the field of geometry, in particular with the arithmetization of analysis. So both share this concern of avoiding magnitudes or removing general magnitude from the foundations. And one can see this here in what I just presented of how he will reconstruct the theory of proportions and similar triangles. So the key idea was to combine how the theory of linear magnitudes obtained intrinsically from the structure of Euclidean plane that characterize Hilbert's axioms. So, and I think this is an important point, so the proof of the geometrical interpretation of the fundamental properties of general magnitudes as geometrical theorem was then a critical step in the modern shaping of Euclidean geometry. I think this is something that distinguished axiomatic geometry by the beginning of the 20th century from previous presentations of geometry. So the proof of the geometrical interpretation of fundamental properties of magnitude. So these are theorems. Then, from a conceptual point of view, I think that a fundamental aspect of the program of constructing a new dependent foundation for Euclidean geometry was a transition from a metrical and informal to an abstractionist understanding of geometrical magnitude. This means that in Hilbert's system, for instance, so geometrical magnitude is not anymore identified with this measure numerically expresses, but instead it's just introduced by means of a definition of abstraction using equivalence relations defined in strictly geometrical terms. So we have a different notion of magnitude, and this is essential for the modern shaping of Euclidean geometry. And finally, just to maybe to come back to the starting point, so we have this very well-known idea of Bolzano, or maybe this is the starting point of the movement of the arithmetization of analysis, where he, this work he's presenting a new proof, analytic proof of the intermediate value theorem. And in this very famous passage, he says the following. So if one considers that the proof of science should not merely be confirmations, but rather justifications, that is presentation of the objective reasons for the truth concerning, then it is self-evident that the strictly scientific proof or the objective reason of a truth withhold equally for all quantities, whether in a space or not, cannot possibly lie in the truth withholds merely for quantities which are in space. So basically, the idea is that you cannot justify appealing to something that is true for a geometrical magnitude and extend this to all kind of magnitude. So I think that what is interesting is that the modern axiomatic foundations for geometry also rejected the inverse direction. So one cannot go from the general to the particular geometrical case. So a proof that appealed to principles of general magnitudes did no longer provide justification for a geometrical theory. This was the key idea. So now the source of the justification rests strictly in the geometrical actions. This is where you can find a justification, and particularly in the structure characterized by these actions. And I think that in this sense is that one can say that the emergence of modern axiomatic geometry was also part of the end of the paradigm of mathematics as the science of magnitude. Well, thank you very much for.
We have 32 minutes for questions.
At the very same time, or roughly the same time on, the theory of metric spaces was being developed, and in part by some of the same people. And so I was a little bit confused by the quotation from Herder, which seemed to be saying that the axioms of geometry precede the axiomatization of magnitude, whereas when we learn about metric spaces, the numbers are taken for granted, and the geometry of the metric space depends on the pre-existing and basically unquestioned theory of numbers. The other question, also around the same time, Hensel was developing around the time he developed Archimedean complete fields.
Sorry, who?
Hensel was developing Peano numbers, which are, I just checked, not at the time, but certainly now are referred to as non-Archimedean complete fields. And I'm wondering whether there's some, whether these developments made reference to this thinking about magnitudes.
Okay, thank you very much. So, yeah, regarding the first point, so I think Herder what was really important from a conceptual point of view for this construction of a new axiomatic foundations for geometry, in the sense that what was crucial for a foundational point of view for the people trying to present just an axiom system for Euclidean geometry is to understand now what should be the relation to the axioms of general magnitude. Shall we just presuppose these axioms as a background in the theory? How should be incorporated in an axiomatization of Euclidean geometry? And what he suggests here is that if you want to show that your axiomatization of geometry is adequate or is correct, you need to be able to prove from your geometrical axioms that the different kind of geometrical entities, there is line segments and plane area, volumes, satisfies all the properties that he axiomatizes in his axiomatization of magnitude. And also it was crucial from a meta-theoretical point of view, which are the necessary and sufficient conditions to prove that, for example, plane area, to prove from the axioms of geometry, that plane area satisfies all axioms for general magnitudes. So I think this is the sense of this sentence. It's not that geometry comes before numbers or some, in this sense, that just presenting how now the two theories should be related from a.
Do you think that these considerations were relevant to Hilbert spaces, for example, or metric spaces? Or was this a completely independent development without reflection, without?
Yeah, I wouldn't know how to answer to that. It's I'm just restricted to the case of elementary geometry. I guess it must have some implication for for the other mathematical development. But I think what I'm trying to suggest here is that this idea, this relation between how you connect or how your geometrical accents are able to prove that plane area constitute a class of magnitude was centrally in the way he was axiomatizing geometry. He was choosing which accent, which propositions you can take as axioms or not. And in this sense is that, the axiomatization of abstract magnitude was really important for the shaping of modern Euclidean geometry. But I guess there must have been some connection. Thank you.
So next it's me here. Thank you for your talk. It was very interesting. I have two questions. One is a clarificatory, maybe something that I missed when you started talking about Hilbert's work. It seemed to contrast Hilbert's axiomatic approach with the synthetic approach, saying that Hilbert was not synthetic, but then as you continue to talk about Hilbert, you mentioned the word synthetic again.
Yeah.
I didn't miss this.
Should I reply first?
I don't know.
So. Yeah, I reply first to this. So I think this is thank you very much for the question. This is a very, very important point. And essentially, this distinction, it has to do with the idea that the main idea of Hilbert reconstruction of the key point is that you can derive the structure of another field from the geometrical axiom. So it's the structure of the other field that gives you the definition of proportionality and then similarity and of plane area. And then one can start to think whether this notion, which is an algebraic notion, is essential or is an alien or strange to geometry. This was the main question. Of course, he shows that this structure is derives or is obtained from the structure of Euclidean plane, but still is a. So at the same time, there were just other approaches which just focus they not present an axiomatic presentation, but just a reconstruction of proportion theory. And there they just provide an alternative definition of proportionality using the theory of congruence of angles. And then so proportion was defined in terms of congruence of angles and some geometrical configuration. So there is no use of the field structure. So that was the main. But then I think it's a really interesting issue to discuss. What if Hilbert is strictly synthetic or no? I guess it depends on what you call synthetic.
Yeah, thank you. And the second question is this relation between or the emergence of a structuralist view, as you explained to us, and the relation of this emergence of a structuralist view with the rejection of the view that mathematics is the science of quantity, when this is some kind of they had to come together or whether they could have been separate. And a follow-up on that question is what is involved in this structuralist view of mathematics. So you indicated, so one thing is that you create structures. So for example, the structure of a real ordered field, but is there also some methodological aspects in such a structuralist view? I don't know if this question makes sense.
So I think so. Yeah, thank you very much for the question. So it was just a final thought. So I was trying to come up with an idea of how Hilbert's approach is related to this issue of justification of why is that in a geometrical proof if you use, if you appeal to a general principle of magnitudes, that this is not this proof does not present a justification of the theorem. So this is, for example, very clear in this passage by Schur, where he say, okay, if you prove that a polygon cannot be equal in area to a proper part, just using the principle that the whole is greater than the part, then you did not provide a proof. And what I think that when Hilbert approaches this issue, basically his response is that, well, the justification now of geometrical theorems are just the purely geometrical axioms. But more precisely, when you see the reconstruction of the theory of proportion and similarity, the justification is just in the structure that is defined by the geometrical axiom, in the structure of Euclidean plane. And this is what I think was the result of this investigation, although Hilbert did not put it in these terms. So I think that's the how I see the relation.
Okay.
Yeah, two independent remarks. The first one is very, very short. I think that in the second part, the part of Hilbert, I would also. In the second part, the part of Hilbert, I would also underline that one of Hilbert's aim is come back to the structures, look at the element where magnitudes are not there. There is an essential dependence between just and so you see the agree with your contextualization, but I think that I don't know. This is Mr. Remark. Then I don't know what you want to say. Well, let's go to the second. The second, I would still consider the part of it. Because that's the first part of your presentation. I would distinguish between two things that is being put together. There is under the title of automation of analysis, you identify the elimination of magnitudes for the solution numbers. But I think that this is only one element that tries to be distinguished by another one. If we agree that the limitation analysis starts in some sense with Cauchy, we cannot forget that Cauchy begins the curve analysis by saying that we always take the meaningful number in the sense that is used in arithmetic, where the number arises from the absolute measure of magnitudes, and we will only apply that as quantity to the important or negative number, etc., etc., etc. So for Cauchy's spirit is the idea that number are measure of magnitudes. But what Cauchy does essentially with respect to Euler and the Lagrange analysis is to find the notion of function or the notion of real numbers. So function is not an automatic notion, but before you characterize the notion of magnitude, and then you define it. And the second volume of consideration is called the real function. And the notion of real function would be nonsensical in the Euler and Lagrange story. So there are two movements: magnitude independent of numbers, but it does not begin with Cauchy, is something that appears later, and function independent of number, and this is already something that begins from Cauchy. These two things I think that should be distinguished and as the important element of the arithmetization of analysis process.
Okay, thank you very much, Mark. Yeah, the second point, I completely agree. Yeah, this part is kind of very broad in order to make room for other, but I agree that these two elements should be distinguished and mentioned. And concerning the first point, I think that the main issue, yeah, of course, in the first part, in the first four books of the elements, you don't have the theory of magnitude, it will come in the fifth book, but what you have is an essential use of the common notions. And this is, for example, what Hilbert wanted to avoid. In order to axiomatize geometry, you need to incorporate kind of geometrical versions of the common notions in the geometrical system. But not assume them as axioms of geometry, but prove the geometrical
You
interpretation.
bring that the use of common notion of the sort of contamination of the notion of magnitude, so the is what you.
Yeah.
So you made me aware of a lot of connections I was not aware of before, so thank you for teaching me. Now this raised a number of other questions. So there were a number of, so maybe my question is totally ill-posed. If so, just call me out for it, right? If it's nonsense. So there were many other things going on in the 19th century. So we have rise of projective geometry, we have the axiomatization by Pasch, we have like the line of Helmholtz, Lee, Klein, group theoretic studies of geometry. So was there any interaction at all between what you have sketched and the other developments, or was this line of research and development basically autonomous?
No, of course, this was a very complex process, and Hilbert's, in particular, Hilbert's work really relied on all what was going on in the field of synthetic projective geometry, the very formulations of the incident axioms, of the order axioms, and also the idea of providing an independent foundation for geometry. It also depends on the idea of providing an independent foundation of projective geometry independently of metrical considerations. So in the notes for lecture courses, Hilbert mentions all the time von Stahl, but also some other projective geometries, and also Pasch. This was very, very important for the process. But I think that my point is just that to say, well, there were other important foundational discussion that contribute to shape this idea of synthetic foundation, axiomatic foundation for Euclidean geometry. And maybe it's interesting to know that these were not occurring necessarily in the field of geometry, but in other field. And regarding Helmholtz and the group theoretical approach, Hilbert was also interested in this and contributed in other works, which are just supplements of foundations of geometry. So yeah, there was these were also important developments for me. But thank you very much for.
Thank you. I think I have the next question. I find the history that you're developing very fruitful and philosophically significant. There are kind of two different ways to think about it, though, that maybe you don't have an opinion, or maybe you do. One idea is that the autonomy of analysis came first because of a kind of disarray analysis. And then in geometry, there was a reaction to that. And that kind of fits with the timeline in the sense that it seemed like the geometrical emphasis on autonomy and purity came later in time. But the other way to think about it would be that, no, both domains had their own reasons to establish this kind of autonomy and purity. And so the timeline is not really important. So then there would be some sort of distinctive reason that the geometricians wanted to have autonomy or purity from this earlier way of thinking about geometry. So it's kind of speculative, but I just wondered if we had any preference in terms of those two models.
Yeah, thank you very much. Yeah, I think it's a very, very good point. I think that if you see the timeline about all concerning these works on the new foundation for the development of a theoretical theory of proportions, that already started by the mid of the 19th century. So I would be more inclined to say that were kind of simultaneous concerns of development an autonomous foundation of each of the theory, not that one comes first and then the other the second. But my very kind of speculative idea is that also by this time there emerged a modern notion of what is a foundation of a theory, and was something that the geometrists were trying to do. And well, in the case of analysis, they provide an idea what does it mean to provide an autonomous foundation for a mathematical theory. And in this sense, I think they were informed by this discussion. Thank you.
So there's a question online, which you probably want to take the questions in the room first because of technological confusion.
Thank you for the talk. I have a brief question about the theory of content. I want to know what this is, how it relates to development of geometry.
So it's not the content of sentence or of theorems, but it is basically the theory of plane magnitudes and spatial magnitudes. So plane areas and solids. And what this theory consists basically is that they provide different geometrical interpretation for the notion of equality of area and equality of volume. You can have different equidecomposition or equicomplementability, different geometrical notion. And then they explore under which conditions these different notion of equality are equivalent or are coextensive. So for example, in the case of plane areas, Hilbert had two notions. One is called equidecomposition. It's that two polygons are equal in area or equidecomposable if you can decompose them in the same number of congruent figures in pair. And then he has another notion of quality of areas called equicomplementability. And it's these two polygons are equicomplementable if you can adjoin to them equidecomposable polygons such as the resulting polygons are equidecomposable. And the point is that these two notions are equivalent only if you assume the Archimedean axiom. So there was a meta-theoretical reflections of which are the and the point is that you need these relations to prove from the axioms that, for example, surface area is a class of magnitude. So this was basically proposing different geometrical interpretation for the notion of equality and then studying which are the necessary and sufficient conditions to prove that these are a class of magnitude.
Thank you. Interesting.
Are there any other questions in the room? Okay, do you know what I need to press? My confusion.
Hi, Giovanni. Can you hear me?
Yeah.
Okay. First of all, thank you for your talk. That's a huge work you've done. And to be concise, on one slide, you provided a quotation from Hilbert's Grundlagen when he declares what should geometric axioms should be. Let's focus on the simplest magnitude, I mean the line segments. They are totally ordered and the order is compatible with addition. And Hilbert declares that these properties have to be derived from axioms. In geometry, they have to be derived. In fact, they are derived from the partial axioms of betweenness. However, at the same time, when he provides axioms for real numbers, the total order of real numbers and its compatibility with the addition is taken for granted. I mean, it's an axiom. So why is it so? In geometry, these properties, the linear properties, have to be derived from axioms, and in real numbers, they are just axioms. The point is that in the Euclidean geometry, in Euclid's geometry, it's the case that the line segments are totally ordered, and the order is compatible with the addition, and it's taken for granted. So you've got two options and no ground to decide it. And generally, I think you follow the German propaganda in philosophy of mathematics.
Thank you very much. Yeah. Well, but you know, I'm a philosopher, not a mathematician. So I will I will trust on what Carlson said in his book. The point is that, so in the case of line segments, so you have an axiom which is not exactly transitive property, or segment congruence is weaker. And then the total order is derived from this axiom of angle congruence. So he needs, of course, he assumes that from these axioms, you prove that the set of segments is totally ordered, but not necessarily from the axiom of congruence of segments. So yeah, in a way you're assuming, and I think so, for example, Schur said it in this word about in the case of line segment is, in a way it's evident that these are magnitudes, and this is why you can assume it. So only for the case of segments. But I think that, yeah, I wouldn't say that he just assuming it in the axiom, but he derived it from using this axiom for congruence of angles.
That's right. In geometry, it is derived. In my opinion, it is derived from the partial axioms. However, in the axioms of real numbers, these are axioms. So Hilbert declares that in geometry, they have to be derived, but in the axioms of real numbers, they are axioms. And the point is that in the Euclid elements, these are just axioms. That's the point.
Okay. Thank you very much.
Okay. If there are no more questions, we'll thank the speaker.
I have a question, but it's still informed. Issues that are great.
Yeah, I think low battery. I know, there's no battery. I was like, don't use it. Maybe we should like get it or something.
Questo quello buono, the accents from nine directly inside of it. Might have had that effect also, like, so that, I don't know, it's just like the house. It's people that are trying to find actual it's just very simple. It's who are the people that comes Yes, so guy, he also read it. Solamente si necesita e anche vedere dice oh chi dice lo sto uno dove che mi dico claro, però sicuramente non iPhone 9, iPhone X. Grazie. Allora, io non ho permesso di stare. Hai un po' di questo tempo. Claro. Esto significa
quelli delle riunioni.
esto è una maniera di quale fotografia la fotocopia della questa definizione è quello di comprare alla proprietà della funzionalità non sono i simboli. No, i numeri, i simboli sono anche quelli lo definiamo sono qualche libro. No, perché però c'è un modello però lo esci la definizione della la nota della che corrispondono con la barra potrebbero essere io scrivo ma non che servono ai secondo me la logica non vedo perché nel senso esatto tiene che avere algo sulla 100 milioni